All right. So welcome to the second part of this morning session on TDE theory. And we have Michael Kesden to talk us about the distribution of inclination of tidal diffraction events in Kerr black holes.
Excellent. Thanks so much for the technical assistance, and thanks for inviting me. I've really enjoyed being at the workshop this week. I'm going to follow Carmel's example, so feel free to raise your hand, chime in with questions during the talk. This is some work I've done with Tom and Joan Singh, who's a really talented PhD student of mine at UT Dallas. We put the paper on the archive just on Friday, so you're welcome to consult that for more details. And so this is kind of, I guess, the real motivation for this was focusing. We've heard a lot about TDE rates, and of course the overall rates are very important. But you can think about what is the distribution of inclinations in tidal disruption events. And so I'm going to talk about what I mean by inclinations, some brief motivations for why we care about inclinations, and then show how, depending on your assumptions of the model, you can get very different predictions for what those inclinations might be. So at the outline, okay. So we know we're talking about general relativity here, black hole spin. I don't know what a non-relativistic spin is like, but when black holes are spinning, and you generally expect them to be spinning because they won't have perfectly zero angular momentum, then the black hole spin intrinsically breaks the spherical symmetry of the Schwarzschild geometry to an axisymmetry of the Kerr geometry. In that, if you're considering Kerr geodesics, they will have both conserved z component of the angular momentum and are Carter constants. And you can derive the analog of the inclination. This is the cosine of the inclination in terms of those geodesic constants. And this asymptotes at large radii to the traditional inclination angle, where you think it's the angle between the black hole spin and the vectorial, Newtonian orbital angular momentum. I'll briefly talk about why do we care about, some motivation why we care about TDE inclinations. Then in terms of talking about rates, obviously we all know to produce photons, optical photons, is a highly non-trivial process, as we heard in Clement's previous talk. But I would say if certainly not sufficient conditions, but necessary conditions to have a TDE is number one, you have to disrupt a star to have a TDE. That means your angular momentum has to be below a certain threshold. D means disruption. And that threshold will depend on both the spins and your inclinations. And also you have to avoid capture. In GR, black holes have event horizons. If you fall directly into the event horizon, you're going to have a hard time getting optical photons out to the observer. And so these are sufficient conditions. And so essentially these set the loss cone, the set of orbits on which observable disruptions might happen. And then the rates at which TDEs do happen is how often those orbits are being refilled by various processes. And that refilling process, once you've broken the spherical symmetry, you can imagine kind of the two extreme cases. Either it's inclination preserving, so that essentially as you migrate, diffuse from outside the loss cone, inside the loss cone, your inclination is preserved, or the opposite extreme is that diffusion, generally diffusion just from stat map will isotropize things. And so you'd have an isotropic distribution of inside of loss cones. And so under these assumptions, we're going to look at both what is the total distribution of these TDE inclinations and these limits, and what are the total rates of the TDE as well, which is just the, the integrated over the inclinations, and then we'll summarize. Okay, so, Kerr geodesics. So the traditional black hole, there's a Schwarzschild black hole, it's spherically symmetric. You've got a nice point singularity at the center. You've got a Schwarzschild radius. You've got an event horizon. Once you introduce spin, I'm not going to talk in general about what supermassive black hole spins might be. There's many theories. Numerical, if you think that, I think in the traditional law, our supermassive black holes gain their mass both through a mixture of major mergers, that two black holes merge to form a bigger black hole, and gas accretion. Numerical relativity tells us in major mergers, the typical black hole spins are about 0.7. It depends on the mass ratio and the inertial spins, of course, but that's a rough ballpark. In terms of accretion, it depends whether it's radiatively efficient, radiatively inefficient, et cetera. There's this infamous, if you have thin disk accretion in the equatorial plane, Kip Thorne showed in the 70s that you could spin all the way up to 0.998. So and certainly observations have also suggested that we might have very large spins, or not either experimentally ruled out or theoretically unusual. So then once you have this spinning Kerr metric, the symmetries of a Kerr determine, the orbital constants along geodesics. So the Kerr metric has time translation symmetry. And so by, Nether's theorem, that's going to leave a conserved quantity, namely the conserved energy. And for the purposes of studying these geodesics, if our stars are coming from the influence radius and our typical galaxies have velocity dispersions much, much less than the speed of light, for relativistic purposes, the specific energy we know equals mc squared. The energy per unit mass then E over m is c squared. And in units where c equals 1, you're going to have 1. So we're considering this is what we mean by parabolic geodesics. And it's going to be very close to 1 in these units. The axisymmetry of curve at its rotation axis gives you a conserved z component of the angular momentum. It's highly non-trivial to understand, but there's this rank 2 killing tensor of the Kerr metric that Brandon Carter discovered in 1968, and that implies you've got this conserved thing that in his honor, they named the Carter constant, that at least in the Newtonian limit, far from the black hole, is kind of the magnitude of the angular momentum perpendicular to the spin axis. And so in terms of LZ and Q, which are relativistically defined constants, you can define basically the magnitude of the orbital angular momentum L and the cosine of the inclination. And so these are kind of the 2 parameters we're going to be looking at. Why do we care about inclinations? Again, I shouldn't have to preach that to this crowd. Kind of the earliest thing is just the idea of the bolometric kind of radiative efficiency potential of your TDE. It depends strongly on inclination. This is a plot showing, this is A over M, the dimensionless spin, what I'm calling chi. 0 would be your Schwarzschild black hole. 1 would be your maximally spinning hole, above which you'd have a naked singularity and you wouldn't be a black hole in the first place. And this is a coordinate dependent kind of radii, but you could kind of choose that as a proxy for binding energy. And we see that for these dash things are the direct or prograde orbits. They're becoming, have smaller prograde radii for the ISCO. What he's calling R marginally stable, that's what we now call the ISCO. And so for the prograde ISCOs, it's getting small. For the retrograde ISCOs, it's actually getting larger as a function of spin. And so the energy difference between these orbits, it's from, it's like 0.42, I think, for the prograde maximal spin, and like 0.04 or something so almost an order of magnitude difference in radiative efficiency. Stream collisions, as we heard, one of the, Tom did a great job talking about that 4-step process of, how we arrive at accretion disk. And the second step for him was stream collisions. And in general, if you have got an inclined TDE, there will be nodal precession that would, delay stream collisions and certainly could have observational consequences. And finally, we've heard lots of talks about, QPOs and QPEs. QPEs, certainly in LS's model, having a precessing disk may be critical for introducing some of the non-regularity and the non-regular QPEs. Jets in general, there's theory to suggest that the jets may be aligned with the orbital angular momentum of the disk, not with the spin of the black hole. And so in the general case, those are misaligned, the spin can precess. People have seen some indications of spin precession in like Swift J1644 and things like that. So there are many numerous reasons we would care about these inclinations. So again, so now just, how does relativity change the picture from GR? So there's tidal disruption, which we do have in Newtonian gravity. We think of kind of tidal forces and, different force strengths on different sides of a finite size star. In GR, you imagine that obviously it's an extreme mass ratio, your star is moving along some central geodesic. Perpendicular to that 4 velocity, you can have a spatial 3-dimensional spatial hypersurface. And essentially what this is the geodesic deviation equation. If X is kind of 2 neighboring geodesics and U is the 4 velocity along the central geodesic, geodesic deviation equation tells you essentially that this tidal tensor C is going to tell you whether nearby geodesics either diverge, which is the analog of tidal disruption, or come together, which is the analog of squeezing. If you look at this minus sign here, this is a real 3×3 tensor that depends on the Riemann tensor of the spacetime, which depends on the black hole spin, and it also depends on the 4 velocity of your geodesic, which depends on both the energy and the inclination of your geodesic. And looking at this real 3×3 tensor, it's going to have 3 eigenvalues. It's going to have 1 negative eigenvalue. So negative times negative is positive. That's the stretching direction. And 2 positive eigenvalues, you're squeezed in the orthogonal directions. And so essentially our criterion for tidal disruption is when that negative eigenvalue, essentially its magnitude across the finite size of your star, exceeds the self-gravity of your star. That would pull your star apart. And so this relativistic condition, where this is the negative eigenvalue of this tidal tensor, determines the threshold angular momentum below which you get tidal disruption. And again, that depends on the spin of your black hole and the inclination of your orbit. And this is generally going to scale as the 2/3 power of the black hole mass.
Can I just ask
Go ahead,
a question?
go ahead.
In this formalism, you considering just a star made out of individual particles, or there is room for the pressure, the role played by the pressure?
This is almost like just a generalization, just the good old fashioned tidal radius is, M black hole over M star with 1/3 R star. Yeah, I mean, if there's going to be this beta D is essentially a structure parameter. This is like an order unit structure parameter. You're right. Depending on the pressure of the star, that can change this threshold by orders of order unity things.
But dynamics is just gravitational dynamics here.
Yes, exactly. This is in the same way that the standard tidal radius is gravitational dynamics, so is this. So this is the kind of your angular momentum has to be less than this threshold to get disrupted. And then to avoid capture, again, you have a motion from the geodesic equations. You can kind of show where you go from having, it's not the ISCO, which reverse to circular orbits. We're again assuming the stars are on nearly parabolic orbits, but there's a threshold angular momentum between you just go to pericenter and go back out again to infinity, and where you go directly into the event horizon. And that is also going to depend on your spin and inclination. And since GR is a scale-free theory, that will go linear in the mass. And so our criterion for tidal disruption is our angular momentum has to be in between. It's like a Goldilocks scenario. You have to be small enough to get disrupted and large enough to avoid capture. Okay, so we're going to now talk about what are the TDE rates in the full loss FLC full loss cone limit. So what are we looking at here? So in the full loss cone limit, and this is just a kind of kinematic factor. So each of these plots, and we're going to see a lot of these. On the x-axis, first again, I'm using units where g equals c equals 1 that relativists like. On the x-axis, I have the magnitude of the angular momentum squared divided by the black hole mass squared. And so for pure GR things, this is a dimensionless thing that's independent, scales independently of the black hole mass. And on the y-axis, I have the cosine of this inclination angle. So cosine goes between +1 and -1. When the inclination is 0, cos of 0 is 1. When the inclination is pi or 180, the cosine is -1. So essentially the things, this is the fully prograde guy, this is the fully retrograde guy, and things are in between. And so just in Newtonian gravity or in neglecting spin, we know there's a sine theta, d theta in spherical coordinates. You're going to have a flat distribution in cos iota. And from the kinematics, you're going to be flat in L squared. So in the full loss cone limit, essentially this rightmost set of curves are the disruption threshold. So everything to the right of here is outside the loss cone and just does not get disrupted. This left set of curves is the capture threshold. Everything to the left of these capture curves is directly captured. And so essentially in the full loss cone limits, the TDE rate is going to be proportional to the area between these curves. And the blue curves are for a Schwarzschild black hole, a dimensionless spin of 0. So obviously when the spin is 0, inclination means nothing. And that's why all these blue curves are vertical. And as you go, there's a green dotted, red dot dashed, and purple dashed curves. Those are spins of 0.5, 0.9, and 1. And so what you'll notice is for non-zero spins, these curves are tilted. They're not vertical anymore. So you have an inclination dependence. And not only are they tilted, but furthermore, they're larger for retrograde guys, negative cos iota, than they are for prograde. And so this is saying that essentially tidal forces are the tilt of the right curves here are saying tidal forces are stronger on retrograde orbits. So if it was all you cared about was tidal forces, you'd expect a retrograde bias in TDEs in the full loss cone limit. But to survive capture, you also have to be to the right of these guys. And these guys, the slopes of these guys are even more tilted than these guys are. So you also have a retrograde bias for capture. And since surviving capture is kind of the complement of being captured, there's a prograde bias to avoiding capture. And so it's kind of a tug of war. What your inclination distribution will be is a competition between the retrograde bias of tidal disruption and the prograde bias of avoiding capture. And that battle, the outcome of that battle depends on the black hole mass. So for capture, which is a purely kind of geodesic phenomenon that is scale free, if you scale it properly by the black hole mass, these capture curves, I'm changing the x-axis here, but these capture curves are independent of black hole mass. Whereas since for disruption, the angular momentum goes as m to the 2/3, L over m, 2/3 divided by 1 is minus 1/3, and you square it is minus 2/3. And so as we increase black hole mass, these disruption curves are essentially moving to the left. And so what we're seeing in these 4 panels, this is 10 to the 6.75 solar masses, then the 7, 7.25, and 7.5. So as we increase the black hole mass, the capture curves remain the same. The disruption curves are moving to the left. And so we see as you move to the left, there's less area between the curves, so there's less phase space for having an actual TDE. And because of the differing slopes of these curves, by the time you pass about 7.25, the curves are actually intersecting with each other. And they're intersecting each other on these retrograde orbits. So you no longer can get, for these spinning holes, you can no longer get, once the capture radius is outside the disruption radius, you can't get actual observable TDEs anymore. And as you go to increasing the higher masses, once these 2 blue curves coincide, there's nothing left. Short shields black holes can't do it. This is showing 0.5, 0.9, and 1. See, there's for 0.5 at this mass, there's a tiny sliver of parameter space where you can get TDEs. And these are going to have a huge prograde bias. And ultimately, to large enough masses, you got nothing left.
Is there for what type of stars? Solar mass stars?
Yeah, solar mass stars. And so the captured curves have nothing to do with the stellar radius. Those are just geodesics. For different stars, you have both different masses and radii, of course, and that beta, I was using this Gia shown beta D equals 1.9 from the different stellar structures. You can, incorporate that with the different order unity beta variant. Good question.
What's the, sorry.
This is going to be a pretty random question.
Let's see what you think about that after I answer.
Okay, so I'm just curious. So if you have a sufficiently massive black hole, there's no tidal disruption.
Right.
Imagine a star comes in and part of the star's orbit brings it inside the ISCO and part is not inside the ISCO. I mean, that's very fine tuned, but you can do that.
Yeah,
so what actually happens?
So that's a great question. So first of all, when you say ISCO, ISCO means innermost stable circular orbit.
Yeah, sorry.
You mean like marginally bound orbit is what that's what Tucholsky called it back in the day.
Yeah.
And so there is actually a threat. Those are not the same thing. So the marginally bound guy has a lower angular momentum than the ISCO. So that the fact that there's a gap between the ISCO and the marginally bound means that if they were right on top of each other, you'd say, oh yeah, my thickness of my star means I can be but because there's that gap, even you're not necessarily going to decide it's a circular one. I actually looked at, you could easily imagine that, if you get tidally disrupted, I looked at this in a much earlier paper. Some fraction of it could go, and get captured, and some, other bit could, if it's a perfectly parabolic guy, the stuff that avoids capture is going to be on the unbound orbits and go out to infinity. But if you had your Hills mechanism, or your binary black holes, or if you wanted a more bound orbit, you might be able to, have some fraction of the star's, envelope avoids direct capture. It's going to be probably a fairly finely tuned part of parameter space for that to be happening. But very good question.
Just a quick question. I was curious to understand what is the physical significance of the mass at which these 2 lines coincide. What is actually happening?
So this is saying, so again, where the things coincide is going to be inclination dependent when you've got spin. Essentially, you've got you need to have an angular momentum below a certain value to get disrupted. And you have to have an angular momentum above a certain value to be captured. But since those 2 angular momenta thresholds scale differently with black hole mass, once you go to high enough mass and they coincide, you can't simultaneously satisfy those conditions. So there's no phase space left for a tidal disruption that avoids capture. So when the things coincide, it means that there's no gap between them, that there's no phase space left for disruption. We're going to be seeing a lot of these Kerr plots. So if you don't understand what's on the axes of these plots, don't be shy to ask about this. So we're starting off with the full loss come limit. And we're kind of agnostic about how the loss cone is being refilled. You know, in the standard kind of old school vanilla picture, it's two-body relaxation from stellar scattering, but other things like resonant relaxation or Hill's mechanism, things could fill it up. The key point is that since these things, initially the stars are on very eccentric orbits generally, whereas the inner boundary conditions depend on relativity. What's going on at 2 parsecs away at the influence radius, it has nothing to do with black hole spin. And so if you've got some alternative mechanism that's refilling those loss, you can have a full loss cone through other things than just two-body relaxation. It's you know, you can decouple that problem from the relativity.
So you were saying before that in the full loss cone regime, the rate will be proportional to the area between these two curves, but wouldn't that actually be, you know, some sort of like a logarithmic factor, being exactly but the fact that right, the feeding rate of stars to the black hole will eventually depend on the scattering rate.
But that's not the full loss cone limit. I mean, that's the you're right. In real, I'm not saying real black holes will have full loss cones. I mean, if whatever, essentially the limit that the relaxation time goes, the refilling time goes to 0. So you're just, you know, maximally populating those orbits. Yeah.
Right. Yeah.
So you get that logarithmic factor, I think, from.
Yeah, but I think, right, in practice, you do care about the replenishment rate, which depends on scatterings, you know, far from the black hole.
Right, and we're going to get to, we're starting, well, I mean, we walk before we can run. I'm going to talk about empty loss cones later in the talk, but I'm starting off with the full loss cone.
Yeah, I just wanted to.
You're absolutely right. Yeah. I agree with you completely. The full loss cone limit can be theoretically considered, but this is not the actual physical rates for real black holes. The loss cone is not perfectly full in real life. Yeah, I agree. And also, there's also the separation between what you care about the net rate, which is certainly an interesting thing worth considering about, and just the distribution of inclinations. And even if something is changing the renormalization of the rate, if that thing is happening at large radii and is decoupled from relativity, the inclination distributions themselves will be robust, even if the overall normalization will change. You know, just decoupling. Not that we care about both things. Okay, so if I just say this is just doing the integrate to, you know, what is the area between these curves? Again, these are, now we're looking at, these are the same 4 black hole masses that we saw in the previous plot. And these are just the probability of having cosiota. And cosiota is on the x-axis. So a flat distribution, like for Schwarzschild, of course, it's flat. This blue curve is just a nice, you know, horizontal line of 0.5, you know, the area under the curve is 1. These are just inclination distribution functions. And you see for smaller black hole, and the limit you go to very small black holes where relativity doesn't matter, these things, black hole spin doesn't matter, it asymptotes to a flat distribution. As you go to larger masses where relativistic effects increase, these curves are tilted to the right. So you've got more prograde guys, fewer retrograde guys. And so, yeah, the y-axes are all the same here. So we're getting an increasing prograde distribution in the full loss cone limit. Questions? So then, as Itai is absolutely right, that, you know, in real life, loss cones aren't full. And so you have the standard picture. I mean, certainly there are more exotic ways you can refill the loss cone, but in the standard cone-Kalsrud picture, and you have diffusion in angular momentum space. And so in large angular momentum, you're outside the loss cone. As your angular momentum diffuses, you can diffuse into the loss cone. And there's typically, if you know, per period, you know, if the amount by which you know, diffusion over an orbital period, if that diffusion amount is large compared to the size of the loss cone, then you kind of naturally expect that you kind of, regardless of the normalization, you'd be equally likely in phase space to be anywhere in the loss cone, and you get those full loss cone distributions we talked about before. If instead, as black holes get more massive, the loss cone gets bigger, stellar densities outside them get smaller, diffusion gets weaker, then essentially since you're diffusing from outward to the inward, you'll be in the empty loss cone limit. You'll have a lot more small beta encounters than large beta encounters. And so I'm considering 2 kind of extreme limits of that. One here, IP is an acronym for inclination preserving. And so what I'm saying here is looking at there's a lot of curves on these plots, but the blue and green curves are the same in both plots. And what those are the green curves. This is a black hole mass of 10 to the 7 solar masses. The green curves are the disruption curves. So you need to be to the left of the green curve to get a disruption. The blue curves are the capture curves. So you need to be to the right of the capture curves to avoid capture. And then the cyan, red, and purple curves, these are different. You're going to have a distribution of stellar binding energies in your host. And that's what each of these colors mean. Here I'm normalizing it, it's an abusive notation. Here I'm normalizing by sigma squared, which is the velocity dispersion of your host galaxy. And so essentially, as your binding energy increases, just from Kepler's third law, you know, the higher your binding energy, the smaller your semi-major axis, the smaller your semi-major axis, the smaller your period. The smaller your period, the less time you have to diffuse an angular momentum space. And so the emptier the lost cone will be. And so for the inclination preserving case, we're basically saying your lost cone is emptied, fully emptied below essentially which is ever bigger, capture or tidal disruption. So essentially the curves in the top panel here are parallel to since the green curves are to the right of the blue curves, these are parallel to the tidal disruption threshold. Whereas in the isotropizing case, what this is really showing is because you have this prograde bias in avoiding, disruption or avoiding capture, stars are going to diffuse from, prograde, or if you just like if I spray some perfume in the corner of the room, it's going to diffuse out and spread over the whole room. If I dump a bunch of stars in prograde orbits and those stars are experiencing scattering, they're going to diffuse out onto, different angular momentum orbits. Here in the maximum diffusion limit, you isotropize. And so essentially the cyan, red, and purple curves here are vertical. Reality is going to be somewhere between these two extremes. Probably you're going to be closer to the inclination preserving case, probably for larger mass black holes, and kind of in this isotropizing case for smaller black holes, if I had to guess, but that's work that remains to be done. Questions about this? And so now really the TDE ray, like Itai said, it's again the integration between the boundary conditions haven't changed. It's the integral of the space between disruption and capture, but we have that logarithmic factor that he's talking about now. There's a weighting that's saying as you go deeper into the lost cone and you're emptier, that this weighting factor is accounting for that. And so what does that, now if we look at these specific energies, essentially energy is a proxy for, as we go from the increasingly bound stars, increasingly emptier lost cones in both that inclination preserving and isotropizing limits. We're going to find that so at the low binding energies, essentially we have very low binding energy, very long period, essentially a fuller lost cone. And these two panels look roughly the same. This is that same prograde bias that we saw in the full lost cone case. But as we go to tighter binding energies, there's emptier lost cones. We're finding that in the inclination preserving case, essentially, since these curves are parallel to the disruption curves, if you have a set of parallel curves, the distance between the curves that's what the parallel means. The distance between the curves is constant, and therefore the area, is independent of the inclination. And so you have essentially what this is showing here is you're getting flat distributions in the inclination preserving case. And that's almost like, if there's a tree that falls in the forest and there's no one there to hear it, doesn't make a sound. If your lost cone is so empty that essentially your horizon is still there, but it's in the empty lost, if there's an empty lost cone and there's a horizon there, it doesn't make a capture. I mean, you're losing the effects of the prograde bias of the capture just because the lost cone is empty there. Here in the isotropizing case, the same thing is going on, that you're losing the kind of prograde bias induced by capture because the capture cone is deep, in the empty lost cone gate. But because you have a retrograde bias due to the stronger tidal forces on retrograde orbits, it's actually imposing a retrograde bias on your TDE distribution. And so you have this elaborate dance between the strong prograde bias avoiding capture, the milder retrograde bias of disruption, and then lost cone being in the middle, and all those things are conspiring to give you your true inclination distribution.
So just a clarification question, so by epsilon of 10, what does that correspond to? I mean, with orbital energies, there is always, conventions of signs and whatever.
Oh, yeah, so this is a
epsilon-
binding, so this is, yeah, not negative, binding, these are bound things. I'm using just an isothermal distribution. So
Right.
this would correspond to the specific binding energy divided by sigma squared being 10.
So.
In the isothermal distribution, which, you can
So
always,
say, I mean, just concretely, so say the radius of influence is at 1 parsec, so these are stars that have same major axis of 0.1 parsec.
yeah, I guess, yeah. Yeah. Do you want to say something, DJ?
So I'm thinking, how do you observationally constrain epsilon? Is it,
I mean, I'm gonna get to the integrated rate. That's a good, so, I think the shorter answer is you don't, particularly epsilon is good, L is gonna affect the penetration factor, which in principle is gonna affect your TDE. Since, you don't, I'm just saying you have to integrate them. I'm gonna show you momentarily the integrated things. This is gonna have because you're coming in a parabolic orbit, the energy you gain in the disruption process or lose in the disruption process is going to be much larger than the velocity dispersion of your host galaxy. And so like we've seen the outflows are 0.03c, which are obviously much larger than velocity dispersions of host galaxies. And so yeah, this is just something we're going to have to integrate over. And that's exactly what I did right here. So basically, there is some distribution of specific energies. And if you integrate over that distribution, this is going to be the total inclination distribution in the inclination preserving case and the isotropizing case. So this top row is a black hole mass of 6.5, the bottom row is of 10^7. And we see that the normalizations are different on the y-axis of these plots. In the inclination preserving case, we have a prograde bias, not quite as strong as the full loss cone case, but similar. So here we're showing this is the mean cos-iota. We've got black hole mass and black hole spin. So in the full loss cone case, it's even more prograde than the inclination preserving case, but they're quite similar. In the isotropizing case, you're going to have a mild retrograde bias for these intermediate masses. That's what we see here, mild retrograde bias. As we increase the black hole mass, the retrograde bias is growing because you're having everything is getting more relativistic. But ultimately, if you get to a large enough mass that captures cutting off all your retrograde guys, then you're going to shift back to a prograde bias, even in the isotropizing case. And so finally, so the moral of the story is you can get, you have this intricate dance, but you certainly can get either prograde biases, retrograde biases, or different things in between, depending on how the loss cone is being refilled. This is something that I've added just because it's of interest to people. People talk about what is the maximum black hole mass, capable of disrupting a star. At the very high ends of these, there's going to be a narrow amount of phase space, but it's at least possible. And again, since all these things depend on inclination, I'm showing it as a function of inclination. And so we see, comparing and contrasting the inclination preserving case and the isotropizing case. Again, this is pretty much similar to the full loss cone picture, that as you go to higher inclinations, you can avoid, it's easier because of the strong prograde bias of avoiding capture. At higher inclinations, you can go to higher black hole masses with avoiding capture. This little cusp here is kind of interesting. I don't know if anyone noticed it before. It has to do with just kind of the detailed curvature of these curves here. That in fact, if the most purely prograde case, the inclination of 0, cosine of 1, is not exactly the place where you're most likely to be disrupted and avoid capture. It's actually at a slightly inclined orbit. It's kind of interesting, but it's just the nature of these curves. If you looked at the isotropizing case, essentially it's the fact that diffusion, essentially, the effect of isotropizing is things are diffusing out of the prograde case into the retrograde case. And so if things are diffusing out of the prograde case, and that's set by that L naught, then even if there exist orbits that survive capture, you're going to be diffused off of those orbits, and so you won't survive. And so below to the left, these curves are identical above a certain point, but you notice this kind of gap here, you're kind of getting cut off because of diffusion. You're basically diffusion is emptying out these orbits that would exist in the inclination preserving case. DJ?
So, yeah, I've been used to thinking that the maximum value is 10 to the 8, but you're saying in principle it can go up to 8.4.
Yeah, so first of all, these things depend on, and in easy ways, I mean, you can just scale them, but it depends on the stellar mass, the stellar radius, the this beta D, which is this factors here. So I'm using for these curves, I mean, I could make similar curves for different cases, but for these curves, I'm using a mass of 1 solar mass, a radius of 1 solar radius. And I'm using beta D equals 1.9, which was this value that Guillaume and Ramirez Ruiz had found in these hydrodynamical simulations about 10 years ago.
But these
yeah.
are consistent for like a sort of 4/3 polytropic star. So that still holds up for more recent simulations if it's like a younger, as long as it's not super evolved.
Yeah, and so I'm saying there is certainly a relativity has quantitative effects. So this thing pushes up to 0.845. If you actually look at shorts, not that you should take M sigma relations, have scatter about them. I mean, those things did go up to those higher masses. And also remember, even though nominally it's possible in this case, if you look at, we're talking about things like the area between, these curves is not a lot of area. So there's one thing to say something's possible, and the other thing is saying what is the rate, and you're going to get to that in another minute. But there's not a lot of phase. It's possible, but there's not a lot of phase space for those.
But by tweaking the solar the stars parameters, you can even push it further up.
Oh yeah, absolutely. By if you giant stars with big, the bigger your radii, even in a Newtonian picture, the bigger your radii, the bigger the difference in tidal forces across a larger distance. And so you can push it up to 10 to the 9 and beyond. You can. I mean, it's going to change the observed properties of the things, but generally larger radius stars are going to be more heavy. Black holes will be capable of tidally disrupting them without capturing.
You could combine it with like an expected current mass function to determine what sort of
This
phase.
And so finally, what are the implications for the total rate? So this is in the inclination preserving case, this looks very similar to that plot that Suvi had put up that I had made in that 2012 paper. And again, so 8.45, we're saying you're starting to nosedive, in your rates, even for the very largest spins. But if you look at this curve, the solid black curve is kind of the Newtonian prediction. You don't have event horizons in Newtonian gravity. The fact that the colored curves are below the solid curve, again, these are spins of 0, 0.5, 0.75, 0.9, and 1. This is just suppression due to capture, and you have a big, almost, order of magnitude variability in spin dependence in, where your maximum limit for capturing is. If you look at the isotropizing case, these plots look kind of different. You see there's the blue curves are obviously the same because for short shields, inclinations are flat anyway, that doesn't mean anything. You get this enhancement here because essentially stars are surviving. Well, you get this enhancement because stars are avoiding, because of the retrograde bias of disruption, stars on prograde orbits that avoid disruption are then diffusing to the retrograde side and being disrupted by the stronger forces. So essentially you get kind of a mild enhancement. This is 25% enhancements in the TDE right here. But as I said, your relativity kind of giveth and relativity takes away. Here, you're getting more disruptions because stars that survive disruption on prograde orbits are being diffusing onto the retrograde side and being destroyed. Here, if you compare these guys to these guys, you get a suppression for the exact same reason that stars that in this case had avoided being captured on the prograde side are diffusing to the retrograde side and being captured. So you have a much kind of steeper, less spin dependent cutoff at about 0.74, 7.4, 7.5.
So go
ahead, TJ.
So the reality will be somewhere in between.
Yes, the reality will be somewhere in between.
So let's say we have 10,000 TDEs and we have masses of all of them. Then the way to compare observation with theory would be try to fit some sort of a fraction of IP plus fraction of I. Is that how you would do it?
But I think that like as Brian and Michael pointed out, right, in reality, this will be convolved with the population of stars that are being disrupted. So here, this very sharp picture is actually smeared out by, the virtue of having, different stars.
Yeah, I mean, the shapes of these things, I mean, if I change the stellar mass and the stellar radius, it's gonna just shift these curves left and right and things like that. I mean, it's not gonna flip the spin dependence or
Sort of
anything like
integrate
that.
over all.
Yeah,
stars.
so it's gonna blur, yeah, if you integrate it over stellar distribution, yeah, it would blur out. I mean, it's almost like drop-offs, you'd have, if you assume there's some mass function of stars, when people observationally that, you lose bluer filters as you go to higher redshifts. As you go to higher black hole masses, you're gonna lose, you're gonna be swallowing whole first your dwarf stars, and then your intermediates, you're gonna have like a stellar drop-off at small stellar masses.
So has anybody done, I mean, for 10 to the 9 solar mass black holes, the dominant rate will probably be subgiants and that, or even giants. So that's some interesting interplay then between stellar evolution and
People have certainly-
diffusion timescales. I'm just curious.
That's absolutely true. I think people have thought about that. I could dig up some references for you. Yeah. So, first you can be born with, in like starburst. I mean, one explanation, people see this preference for with a population of young giant stars. Essentially, you're going to be disrupting at larger radii, and so you could have larger rates. Even for older stars, we'll have a red giant phase, and so yeah, you could have for 10 to the 9 solar mass black hole in an older, like a non-starburst population. I absolutely agree. The dominant source of TDEs are going to be, I've got some population of stars that as they evolve off the main sequence and swell to red giants, they're going to get disrupted, and they're going to give you.
Yeah,
it's
and I
gonna be
think
driving
the
the
subgiants will not look all that different from a typical TDE. Red giants look totally different because they're so large.
But I think the problem with giants being disrupted in this standard picture, the lost cone theory, is that they're much more susceptible to
collide.
direct collisions. So it's
True.
not actually clear that you can evolve them to get to these precarious orbits. And
But what about, your 2 solar radii going up the giant branch? So, not 1,000.
yeah, I mean, there might be like some sweet spot in between where you're not like,
And so, yeah, Gigi, I'm working on, the reality is going to be somewhere in between. And I think in general, it's going to be at small masses, I think it's going to be closer to this end. And at high masses, I think it's going to be closer to this end, just because there's lower densities on high mass guys. It's going to be harder to fully diffuse over the things. I'm out of time. I'm on the last slide anyway. So it's
We
a good
should be
time.
getting there, so the next speaker has enough time.
Yeah, so this is just a summary of what I just told you, that essentially to get a disruption, you have to avoid capture and be disrupted. Because of the different, prograde bias of avoiding capture, retrograde bias of disruption, it gives you different inclination distributions. And I think the inclination distributions themselves, regardless of the different mechanisms for revealing the loss cone, as long as those mechanisms are happening in the Newtonian large radius regime, that will affect the whole normalization of the rates, but it won't necessarily, the actual inclination probabilities themselves will be more robust. And so, yeah, you can get both, very different inclination distributions and effects, different integrated effects on the total rate as well. Yeah, so thanks for your time. Thanks for your